Okay. Let's review net ionics. Your favorite thing. Now, I did give you this. It's very last minute AP net ionic equation strategies and how to attack them. These probably won't get you a 15 on question 4, but they will help you beat the national average. So if you get somewhere between 7 and 8, guys, you're doing good. If you hit 11 and 12, you are seriously ahead of the game. You'll probably get a 3 if you fail everything else. Know what I'm saying? You are ahead of the game, and you will get 3. So let's talk about some of the basic things. Your solubility rules come into major play, and there's some things that are other nuances that we do want to talk about. So the big mama. All nitrates are soluble. So if you ever see anything that's a nitrate, cross it off. Cross it off. Big daddy. All group 1 metals and ammonium salts are soluble. That means they dissolve in a solution. You'll never get a precipitate. Halides are soluble except for silver, mercury, or lead. Now, specifically, I do want you to write this in. Which halides is it talking about? Chloride, bromide, and iodide. Now, why am I using the ides? They're all in ionic form. Okay, they're in ionic form. Strong acids, hydrochloric, hydrobromic, hydroiodic, nitric, perchloric, and sulfuric. Write these dissociated. What does it mean by dissociated? H plus Cl minus. Never put them together. Why do you never put them together? Because strong acids dissociate 100%. Except concentrated sulfuric, which is 97%. Now, why is that like that? It's a special word we talked about, and it's because of that little bitty 2. What's that? Yeah, di something. Diprotic. Very good. That's why. So, again, the reason it's 97% is because it is diprotic. It donates how many hydrogens at one time? One at a time. One at a time. All right, so if carbonic acid is formed, this one I would definitely circle, put a little star beside it. Carbonic acid will always produce carbon dioxide and water. Okay, carbon dioxide and water. Strong bases. Write these bases as dissociated. Write these bases as dissociated. So strong bases has hydroxides of group 1 and group 2. Now there's a little star. Where's the star coming at? I don't see it. Anybody see it anywhere? There it is. The little guys, okay? What's wrong?
Is it if carbonic acid is formed, as a product, it's that, or
if carbonic is formed as a product, is it different on yours?
you add that to the product?
No. It would be H2CO3 yields. Come on. Oh, don't walk up on me. All right, anyways, it would be yields carbon dioxide plus water. It dissociates into that. It is. It's just, yeah. But here's the little star because it talks about group 2 metals, and it's down here. The little guys in 2As have solubility issues. Write beryllium and magnesium undissociated. Calcium can go either way. The big guys are soluble. What does it mean by the big guys? Well, and talk about in group 2. So really strontium. Okay. Now, what does it mean by undissociated? Okay. Be and Mg will always be like this. BeOH2 and MgOH2. And also, which one? SrOH2. What do you notice in common? They're all group 2, and they are called what? Dibasic. So if they're dibasic, leave them together. Little guys make stronger bonds. Yeah, don't dissociate them. This one right here. If you ever put group 1 metals in water, what do you get? A kaboom. What does it mean by kaboom? An explosion. And kaboom is a formation of explosive hydrogen gas. So that's why you get an explosion, as you're producing the hydrogen gas. So that's exactly what happens. Any questions? So let me just give you an example of what that would be. So if you had some potassium, let's go even more yeah, look, potassium's good enough. So if I have some potassium solid and I'll mix it with H2O, what type of reaction is this? Single replacement, right? So K is going to kick the H out. So you're going to get a metal oxide, which is K2O plus what? H2. Why is it not H plus? Because what does it say? When you mix it, you're going to produce hydrogen gas, which is very explosive. Water is a weird one, okay? Water is a strange one. All right, going back to this, write all weak acids and bases as molecules, so such as N8. What's wrong? It's not balanced? That's right. So we need to stick a 2 there. Now is it balanced? Very good. You've got to balance it. Very, very good point. Always balance them. So NH3 is a weak acid. We have acetic acid or even HF. That's also a weak acid. Be on the lookout for BF3 and its cousins BCl3. They are classic Lewis acids. So make sure you notice BCl3, BF3. If we're talking about Lewis, what is a Lewis talking about with acids and bases? Remember, Lewis has the E, so it's talking about who? We're talking about what? Talking about electrons. And acids do what with those electrons? They accept the pair. So they gain an electron pair. That's exactly what happens with Lewis acids. So even though they look weird and they don't have the H, they're still an acid. So that's right here. BCl3 and BF3 are still acids because they can gain an electron pair. All right.
Mr. Richard.
Just 1 second, please. Yes, ma'am. I don't know. All right, so turn this puppy over for the attack strategies. So turn it over. This is what should be on the back. Is it? Did I double it front and back? Yeah. Fantastic. Very good. So look to the right-hand side. So here we go. Before trying to figure out the answer, scan the words and do these things. Cross out all nitrates. Circle any word that applies a solid or a gas. Why is that true? Because you can't ever dissociate them. You can't ever break them down. They must be present in all net ionics. So, No. Yeah, I don't know. The only liquid, there are 2 liquids on the entire periodic table plus one that's normally liquid, and that's water. But bromine is the key there. So powder, turnings, chunk, vapor, whatever. Okay, circle those. Cross out any 1A metals you see unless they are with a solid or a gas, such as sodium metal. You with me? You gonna cross that out? No, why? It's a metal. It's a solid. Underline the halides. Why? And then ask yourself if it's with silver, mercury. Now, why these particular ones? Very, very good. So if you cannot cross out the halides, make sure you do cross out the chloric in hydrochloric acid because you dissociate all H pluses. All right, let's see. Circle burned in air or combines with oxygen. When that happens, what do you think? Boom. You get explosions. You get fire. Circle the word concentrated. Now, if they give you something like this and it's talking about coordinate complex ions, congratulations, AP exam, you have fooled us. We don't know what these things are. I don't know of any teachers that teach these at all. They're above the time limit we have, and there's a lot more things that are more important. Okay? So, let's look. Let's make sure there's nothing else on here we want to look at that's important. Halides, group 17, bromide, iodine, chloride. And in this case, it will be fluoride, but fluoride's a little bit different.
If Richard Stern or Chris McCollum is still in the building, please report to the front office.
Chloride, bromide, iodide. BrCl, or Br minus, Cl minus, and I minus. All right. So focus on the reactions you marked. Write the reactant sets for all three. Spend 3 minutes writing the products using solubility rules, strong acid-base guidelines, and all that stuff. So I'm just going to kind of let you look through these. Just make sure you do look through these things at the bottom. They are very important. Metal oxides plus water gives you a base. Non-metal oxide plus water gives you an acid. Metal carbonate goes to CO2 in the metal oxide. So these things are really important. Okay? What's wrong? It's raining. Okay. All right. So let's go into this. So looking at the first one. Now, my biggest suggestion to you is write it as a regular reaction. Write it as a regular reaction because you can cross things off easier if you write it as just a regular reaction. So they tell us a solution of sodium hydroxide. So how would I write that? NaOH. Now, a solution, what state of matter is that? Aqueous. Okay, aqueous is added to a solution of what? PbNO3 what? 2. So, and we know it's got to go to something. And guys, we know what type of reaction this is. What is our reaction type? So double replacement. What are we going to get? NaNO3 plus PbOH. So what we're looking here for, PbOH2. Now, this is where your solubility rules come very, very, very important. What can you cross off in NaOH? Na. You can cross Na off. What can you cross off in PbNO3? You can cross out the nitrate. What about that thing? Oh, that's definitely got to go. Now, here's how we know what's left. According to solubility, hydroxides are always insoluble unless with group 1, ammonium, and CBS. So technically, what has just formed? A solid. So what are always written in equations? Solids. Solids are always written in equations. So to create the solid, what must be left on the other side? They're ions. Those particles must be there in the equation to even get there. So, guys, this should be answered for you. And it should be very, very simple. It should be OH minus plus PB what? 2 plus. Very good. Make sure you get it in ion form. Goes to PbOH2. Now, last, the most important question. Is it balanced? No, it's not. What do you need? You need a 2 right here. That was easy. All right. Now, this is where it can get a little hairy and a little scary, a little weird. The qualitative question. Some of them are really easy. Some of them are really, really difficult. If 1 liter volumes of 1 molar solution sodium hydroxide and lead nitrate are mixed together, how many moles of products will be produced? Assume the reaction goes to completion. So, will there be a limiting reactant? Will there be? There will be. And again, this is why it's weird. We've always said the limit, because what you're doing is you are mixing. So anytime you mix something, one of them's got to do what first? It's got to run out first. All right. So we know it's the number of moles divided by what? By the coefficient. Now, we don't have calculators on this, so they should have made it easy math. How can we get moles from this right here? Okay, it's 1. How do we know it's 1 mole? Because molarity times liters equals moles. Well, what is 1 times 1? 1 mole. Now, so here we go. So for OH, it's 1 over 2, which equals what? 0.5. And so that's for OH. You with me? So that's how much hydroxide will be produced. Well, what about for lead? It will be 1 over 1. So this is how much can possibly be made, right? So if this is what possibly can be made, how much of this can be made? 0.5. 0.5 moles. So 0.5 moles of PbOH2. So anytime we're talking about mixing two solutions, there's got to be a limiting reactant somewhere. Why? Well, something's got to run out. Something has to run out. Yeah. Okay. All right. So that one was fairly easy. I think you should have definitely got the reaction right. Now, how do they score these? Let's go back real quick. Hopefully it'll come back up very fast. The way they score these is, come on. Yeah, the recorder does make it slow. All right. They give you 1 point for the reactants. Okay. They give you 2 points for the products, and then they give you 1 point for the balanced equation. But again, if you screw up the products and you still balance it right, will you still get the balancing point? Yes.
I found that it's really hard to balance if you're just making up everything.
It is. Sometimes it's difficult to balance. Now, please make this note. You balance for 2 things. Very good. I want to write this down, though, for everybody. You balance first for atoms. That's the most important things. And the second one is what? The charge. If the charge isn't balanced, it's not balanced. So, let's look. What is the total charge on the left-hand side? How do you know? You got 2 negatives, 2 positives. Over here it is also neutral. So they are both neutral, so you're good there. All right, moving on to the next one. Nitric acid. What? Yeah, the first one's on there, yeah. Does it look different?
Yeah, we don't have a box.
Really? Oh, I copied and pasted. That's why. I copied and pasted. All right, so nitric acid is added to a solid, ding, 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 solid sodium carbonate. What did it tell you to do when it talks about solids? It says circle them. Why do you circle it? Because that whole thing must be written. So we know that this must be in there. So CaCO3. Make that look a little better. Okay, if it wasn't solid, it depends on what it was with. Okay, because that's when you have to know the carbonate solubility rules. Yeah, CO3 mice. All right, so now we've got to deal with nitric acid. So nitric acid is what? HNO3, correct? Well, what do we do with all strong acids? Dissociate them. So it's H plus NO3 negative. What do you notice is present? Get rid of that sucker. That's a strong acid. Nitric acid is a strong acid. So what can we add over here? H plus. All right. So let's finish writing the equation here just so we can see exactly what we're going to produce in a regular honors reaction. So what type of reaction is this? It's a double. It's a double. So we're going to have H2CO3 plus what? CaNO3. Now, what can we cross off? Oh, yeah. That needed 2 right here. Very good. So that's right there. So what can you cross off? You can cross off the nitrate. But what will that leave you right here? Very good. Ca2 plus. Because remember, we're looking for things that change form. Up here, what is this? It's a solid. Did it change forms? Over here, it's a what? It's an ion. It changed forms, so you have to leave it. All right, so we know we're going to get that. So we know we've got a Ca plus. Or excuse me, Ca2 plus. All right, let's see what else we got here. Now, very good. Very, very. Okay, well, I didn't hear you say that. This is carbonic acid. In the previous thing, it told you carbonic acids always are written into dissociation form, which is what? Water and CO2. Go back and look at the attack strategies. It was on there. Matter of fact, let me just pull it up just to prove it to you. It was the one where y'all made fun of the words. Right. Yes. So if carbonic is formed as a product, you write it like this. That's exactly what where carbonic acid is, guys. Carbonic acid was a product. But instead of writing it, okay, please listen. Instead of writing it as H2CO3, write it as this. That's one of the little nuances of net ionics that kill people. Nuances. Nuisance is your pain in the butt, and nuance is something that's different from the norm. So again, this is the little thing. This is why this attack strategy is here for you. Instead of writing it as carbonic acid, you must write it as CO2 plus H2O. So now we know that. Now, I don't, but I think if you balance it, you'll still get that balancing point. I want to go back into this right here. Here we go. All right. Let me erase this because this is pointless. All right, so we know now that this must be written in as instead of carbonic acid. So it's H2O plus CO2. And again, where did that come from? It's the carbonic acid dissociated. That's how you always have to write it. Now, my last question, is it balanced? No, it's not. That's all you have to add right there is a 2, and it is balanced. So why is it H+? Nitric acid, all strong acids are written as dissociated. And what can you do with nitrates? Cross them off. Why is this written as a whole thing? Why isn't it broken up? It's a solid. Always write solids and gases together. Over here, the calcium nitrate is broken down in just calcium ion because the nitrates can be crossed off. And again, carbonic acid, break it up. Yes, sir.
So say you didn't break it up, you don't get the point something. You don't get rid of the reactants.
Exactly. Exactly. Yep. If you didn't break it up, you would only, like if you left it as this, you wouldn't get the correct product points. I don't think. They may be generous. It depends on the year. They might be generous and give this to you. But if balancing, you should get that point. Okay? All right. Now, let's look at the qualitative. Briefly explain why statues made of marble, which are calcium carbonate, displayed outdoors in urban areas, are deteriorating. What do you mean? These are the exact, that looks different. It's the exact. Yeah, what I gave y'all are the questions I've been going over. All right. Now, why is this occurring? Why are those statues deteriorating? Okay. This is one of those weird, like, what are they talking about questions. Very well. Yes, it is acid rain. Very, very good. Why they are reacting is because when calcium carbonate gets acid rain on it, this H plus from the acid breaks it down. Okay. The key word is displayed outdoors. This is one of those questions you're like, okay, AP, I get there's chemistry here, but I don't know why you're asking me this question. This is more of an environmental question. I get it. We are in South Alabama. That's why I don't. This is one of those, what's the question when they're not fair because of the region you live in? There's a special name for those questions that if it talks about a sailboat, like a part of a sailboat, we don't know what a sailboat is.
I know what a sailboat is.
Or it talks about acid rain. So again, from this equation, can you definitely tell that there is something to do with an acid here? Okay, and we know that acids break down. So what they have written, let me just read you what they have written. It says the H plus ion in acid rain reacts with the marble statues and the soluble compounds of Ca that are formed wash away. So the acid reacts with the marble and it creates this calcium ion that just gets washed away. So it deteriorates. Things you'll never need to know in AP chemistry. But again, it's those type of questions that'll just make you ill. That if it ever asks, and it's got an H plus, talk about the acid and how things dissolve in acid. That's the approach I would have taken with that. All right, last one. Now, guys, again, this is what we're on this sheet, right?
The Detroit is actually dystopian. It used to have a population of 120 billion. Now it's like 7%.
Okay, thank you. Appreciate that geographic lesson. Here we go. Now, this should be very simple to us. Listen. A solution containing a silver 1 ion. So it tells us it's just silver 1, right? So we don't necessarily know what it's mixed with, but we do know it's a silver 1 ion. Then they give us something very important. It's an oxidizing agent. What was our thing that had? Okay, it was ox and Ra and red cat OA. What is this one? That's OA. So we know that the silver ion is going to be reduced. Again, this is exactly how I would set this up. So we know that this is going to be reduced, correct? All right, let's go to the next reactant. Is mixed with a solution containing an iron 2 ion. Now, we already know this, but if we weren't quite sure, that it says reducing agent. That was our ox and Ra. That's why I kept building those things. That's why I kept setting those things up for you. It's so hopefully that when you got to things like this, you would remember this stuff. Ox and Ra. So we know that, ox and Ra. So we know that silver is fixing to be reduced. When it's reduced, what happens to the charge? It goes to 0. So what are you going to form? Silver solid. You're going to form that neutral silver piece of metal. Now, but here's the weird part. Iron is being oxidized. Oxidized means what happens to the charge? It increases because oxidation is a what? Try again. Oil rig. It's a loss of an electron. Well, when you lose an electron, it's got to go up. This is when your skills have to come into play. What is the only thing that iron can increase to? 3. Because iron's only possible charges are iron 2 and 3. What if this was lead? Be lead 4. What if it was copper 1 right here? Copper 2. You have to know those different transition points. What if it was 10? 10-2, it'd go to 10-4. Go back to your polyatomic list that I gave you at the very beginning of the year. All of those are on there. All of those are on there. So it's going to be Fe3 plus. Fe3 plus. This actually should go in the box because you're done. They're all well. This is a solid. The rest because it says in a solution containing. So if you were going to have to draw the electrochemical cell to this, one of them would have to be a platinum cell because none of these are solids, right? So you'd have to have a platinum cell to it, or an inert electrode. You could use that graphite. So this is exactly these oxidizing agents and those reducing agents are going to help you out there. So that's exactly what they're telling you. Now, question II, the qualitative, should be very simple if you get this right. Now, my next question, we always balance for atoms and what? Charge. Is it balanced charge-wise? Yes. What is it? on both. 3 plus on both sides. Qualitative. If the contents of the reaction mixture described above are filtered, what substance, if any, would remain on the filter paper? The little pieces of silver. Exactly. So the silver, little Ag particles. Because it would not pass the filter because it has turned solid. Silver particles. It turns, yeah, you need to mention silver though. You would have to say silver. What they have, it says the precipitated solid silver remain on the filter paper. That's all it says. It says 1 point earned for the correct substance is all it says. I would say silver precipitate or particles or solid. Something to let them know you know it's silver solid. Guys, I think this is an easy net ionic personally. Oh, the one that y'all took was very, very difficult.
The little sheets that you gave us twice because you said you were going to test them.
Yeah.
I made a 0 out of 12 on like every single one.
That's why I want to go over them. That's why we're going over this now. All right, so let's look at the last one. The other one I gave y'all. Guys, what I'm fixing to show looks different, but it's the same thing. I just copied and pasted. Spit on my keyboard. Yep. All right, what's the first question? Chlorine gas is an oxidizing agent? All right. All right, let's work these 3 and we'll call it quits. So this time, chlorine gas. What are you circling and why? Circling gas. So as soon as you see that, what are you thinking? Uh-oh. I'll kick you in your shin if you leave it like this. Very good. It is diatomic. You better not miss those diatomics, guys. Is an oxidizing agent. It may not have anything to do with it, but just go ahead for fun and label it. So it's what? Red cat OA. So red cat. Come on. So now, it should gain a what? An electron. So I'm writing this out. I'm thinking it's definitely going to have to go to this, correct? Somehow, some way. It's got to go to this. Is bubbled into a solution, that's what? Aqueous, of potassium bromide. What group is potassium in? Cross it out. You don't need it. So potassium, cross it out. So, but now, let's just go ahead and down here and let's write the regular reaction just so we know what we're doing. So we have KBr. So this is a single replacement activity or single replacement reaction. Here's the deal. Now, be very, very careful. Cl is going to try to replace what?
BR.
Why is it Br? It's an anion. Very well. Non-metals only replace non-metals. Why will it not replace the K?
Because K is it's not a non-metal.
Perfect. It's not a non-metal. It's a metal. So what we're going to come up with is we're going to come up with KCl plus, if you leave it like that, just jump off a bridge.
BR negative.
B.
I didn't say that.
It's Br2. It is Br2, sir. There we go. Now, yes. Yes. All right, so here we go. Listen. This would be your correct honors chemistry equation if it were balanced. If it were balanced. It's not balanced. I mean, okay. To make you happy, we'll balance it. So I need a 2 there and a 2 there, and we're done. Okay. But again, we can cross some things off. What can we cross off? We can cross both K's off. So we know that Cl2 is going to be plus what? Br minus. Very good. Now, we always look for things that are changing charge or changing states of matter. Is Cl changing charges? Yes, it's being what? Reduced. So it's going to go to Cl minus plus Br2. Is that changing states of matter and charges? Very, very good question. If it asks for states of matter, what would you do? Wrong.
Get it, kid. It's a liquid.
It's a liquid. Okay? Bromine is a liquid. So, but notice in the halogen columns, fluorine, chlorine, bromine, and iodine. They're all halogens, but bromine is the liquid, iodine is a solid. They're not going to ask you for that, but just in case, because guess what? Guess what's coming next? What is that?
More math.
What is S?
Math.
It's not math. It's entropy. So it will help. It will help in your description, correct? It'll help in your description.
It's going to be R2 because the other one would be in.
Exactly. Exactly. So it's got to be, it's because BR is going to kick out by itself, and that's not going to be by itself. Now, is it balanced? Nope, it's not. We need a 2 here and a 2 here. So is it balanced? Guys, you're done. You've completed it. Does it help to write the complete equation? I personally think it does. Does it help you? I really do. I would write the regular honest chemistry version, cross out what you know crosses out, and see if you can see how things move and change. That's the best strategy to attack these with. Sir? If you wrote this, they'd laugh at you and give you a 0 and move on. They may give you a 1 for balancing it right. Okay? But they're going to laugh at you. They're going to say, he didn't learn anything in AP chemistry because... Huh? Yeah, we're going to go there. Okay. So now, let's look at double I. Shh, guys, please. Let's look at double I. So predict the sign of delta S for the reaction. Then says, keyword, justify. What does justify mean? Explain. Okay. So first of all, predict delta S. Now, we know, listen, we know that this is a what state of matter? Gas, because what does it say? Listen, guys, please stop. This is a aqueous because it's a solution. Then this is also a solution. So here's what's happening. We're going to cancel those out because they're not going to matter. But you are going from a gas to a liquid. So is that becoming more ordered or more disordered? More ordered. So delta S is negative. Exactly. So it's becoming more ordered. So delta S is negative because liquid is more ordered than a gas. So you're going from a mole of a gas to a mole of a liquid. However you want to say it. Let me read you what they have. It says the sign of delta S is negative. One of the reactants, Cl2, is a gas, and there are no gaseous products. Gases have high entropies, so the entropy of the reactants is greater than the entropy of the products, making delta S negative. Because aqueous and aqueous cancel each other out. Sir? Okay? If it was a gas instead of a... I'm just throwing hypotheticals in here. If this, for some reason, let's just say it would have been F. F2, that's a gas, right? Well, it would depend upon the coefficients. If it was a 1 and a 1, remember, if you increase number of moles of gas, you increase disorder. Why? But here it would be the same. So delta S would be, there would be no change. There would be no change in delta S. But if this was hypothetically a 2, it's becoming more disorganized. So be positive. Why is that true? Who is... Okay, so let's go on to the next one. Now, what do you see and notice the key word is in B? Solid, very good. So we see the word solid, so we're going to circle it and we're going to automatically write strontium hydroxide. Agreed? Strontium hydroxide. Write it out as a solid because we know, and I would in fact, just to help me make sure I do that, go ahead and write an S. Now, we know that it's strontium hydroxide. That's got to be there. And then it says a solution, so that tells me it's aqueous, of nitric acid. Is that strong or weak? Strong. Always write strong acids how? Dissociated. So it's H plus NO3 negative. What do you see there? Cross out the nitrate. You don't need it. So we know that we're going to have plus H plus. Agreed? Guys, what type of reaction is this? It's acid base. It's still single replace, but it's acid base. And what do all acid base reactions produce? A salt and water. Always get a salt and a water. You with me? All right. So salt and a water. So plus all acid bases. So let me go back and let's write the full reaction, Jada, just so we can see it. So we have SROH2 plus HNO3. Again, this is how I would recommend starting it out every single time. And so we're going to have SRNO3 2 plus H2O. That's how we're going to have it written, right? Now, looking at this kind of should make it a little bit easier. Okay? What can you cross off? Cross off that. Cross off that. Anything else you want to cross off? Nope. So what's going to go in the blank we have left? SR2 plus. Right? So again, I recommend just writing the whole thing out, crossing off what you can cross off. That's exactly what I'll do. Because this is an ion form, right? What's it turning into? Liquid. Is that changing forms or charge? Yes. This is a solid. Is it changing forms or charge? Yes. A salt is the cation of a base and an anion of an acid. It doesn't always have to be a group 1 or group 17 because nitrate's not that. Okay, huh? Yeah. So it must come from the cation of a base and the anion of an acid. All right. So to me, that should be easy, slam dunk, no doubt points. Oh, very, very good, Claire. Thank you. Got to balance it. Now, can I give you a tip? Can I make your life a lot easier? Nope, nope, nope. This we said is a double replacement acid base. So we know that SR is now going to be with NO3, correct? We know that H is now going to be with OH. My highest recommendation, instead of writing water as H2O, my highest recommendation, write it like that. And why? Here's why. Is that the same thing as H2O? Here's why. Because whenever you're balancing, you can group polyatomics together. Is the hydroxide here? Is the hydroxide here? How many hydroxides? And then, there. 100% approved and recommended. Because it's easier to balance that way. It is weird. But matter of fact, in the notes we're getting to, I'm going to start writing it like this. No, they want you to write it like that. They encourage HOH because it's easier to balance. It's easier to see what's going on. I would write HOH personally. Everywhere. If you don't like change, don't do it. But again, it makes it easier to balance to me. If you get used to it, it's so much easier. Okay. Here we go. So let's look at part double I. Now, let's think. I haven't even honestly read it yet. All right. So, how many moles of strontium hydroxide? So we are looking right here. We're looking for so many moles of this stuff would react completely with 500 milliliters. Uh-oh, what's wrong with this? Change it to liters, which is 0.5 liters of a 0.4 molar nitric acid. So I have, now, liters times molarity gives me what? Moles. So how many moles would that be? 0.5 times 0.4? So that's right. 0.2 moles. All right, so right here I have 0.2 moles. Now, why am I asking for, why do I put it there when it says nitric acid?
Because that's how many.
That's where nitric acid should be, right? We've crossed off the nitrate. So, what type of conversion is this? Mole to mole. Guys, if you can't do this, you really don't need to be in this class. 0.2 moles of H plus, where did mole to mole come from? The coefficients. So it's 2 to 1. So this is moles of SR. And again, I'm doing this because I guarantee you somebody watching this video has no clue where I'm going with this. What's the answer? Now, you can explain it. Personally, this works just fine. If you can't do a mole to mole by this point, wow, that's embarrassing. Mole to mole comes from, as a matter of fact, I'm teaching this in honors right now, and they are saying this is the easiest thing they've done yet. Okay? You, again, exact same thing. You will get 1 point for the reactants. You will get 2 points for the products. You will get 1 point for balancing it, and you will get 1 point for the qualitative.
So it's 5.
So it's 5 points. This is a 15-point problem.
What's the other 10?
The first question and the third question. That's why I said in the beginning, if you can get 8 to 9 points, awesome. If you can get 10 to 11 or 12, you are rock and rolling.
So you tell me I'm more than likely to pass, I can do that.
Yes. If you can get 11 to 12 of these, you're well on your way to 3 if you can cover everything else. Because if you know enough rules to make this work, you know enough rules to pass other questions. Well, they're just listening. Hope those crackers and juices are good that you're drinking at home. Grapes, yeah, eat grapes and bananas. All right, last question. We're going to wrap it up here for today. Again, I want to take the approach of writing the entire honors chemistry version equation and breaking it down how we know we have to break it down. So a solution of barium chloride. So go ahead and write it as you know you'd write it. Now, why? Is that correct?
No.
Why not?
Because.
No. Very good. BaCl2 is added drop by drop. Do you think this has really much anything to do with what we're doing? No. Maybe possibly a qualitative, possibly, but nothing with a reaction. To a solution of sodium carbonate. So sodium is Na2CO3, causing a precipitate. They have just given you a humongous advantage because you know something has to turn what? Solid. They've given you a big clue there. All right, so basic honors chemistry. This is a double replacement. So Ba is going to be with CO3. Na is now going to be with Cl. So do the easy one first. NaCl. Is this the precipitate?
No.
Heck no. It's not. So we know that what's going to be the precipitate. Now, why is it BaCO3? Why are there no subscripts? They're 2 positive and 2 negative. So we know that this is the regular honors chemistry equation. We should hopefully be able to know what to cross off from this point, correct? What can you cross off in the first one? Cross that off. What about the second one? Cross that off. Cross that completely off. That changes everything. That makes life so much easier. Jada, you like this, don't you? Okay, makes it much easier. So Ba is a what? 2 plus CO3 2 negative goes to BaCO3. Is it balanced? It is balanced. It is balanced. Now, this is the hard question. This is the hard question, and I'm going to be honest with you. I tried to find how and why to explain this, and I couldn't find an answer that would make this very simple. Huh? Okay. What happens? First of all, is it balanced? Yes. Yeah. This is really simple. This is super easy. You should get all 4 points of this equation. Well, we'll find some harder ones. Okay. Now, what happens to the pH of the sodium carbonate solution as the barium chloride is added to it? So they're asking about this, right? They're asking about what happens to this or what happens to this. So we're on this right now. So we know one of these is either going to go up or one of these is going to go down. If this right here goes up, what happens to the pH? Be very careful. More acidic, which is down the scale, right? Okay. So this one would go up, which is still more acidic. Exactly. So if this number goes down, it's more basic, so it goes up in pH, right? So you're just looking at numbers. But here's the deal. That's the question. Is it how in the world is sodium carbonate and barium chloride associated with a base? Okay? Or an acid. Let me think of how it is. For some reason, and again, this is the part I tried to look up. This is one of these questions you're going to get to like, I have no idea. They are saying this solution is basic. And I'm thinking here's the reason why. I'm thinking this. What is that? It's carbonic acid. What do acids turn into on the other side of equations? Conjugate. They're conjugate base. So I'm thinking that if you were to mix this with something with sodium in it, like a sodium chloride, somehow, some way, you're going to get the conjugate base, which would be sodium carbonate. So it's a conjugate base. Again, this is one of these weird ones. They're saying that it's basic. So, since it is basic, what is forming? A solid is forming, correct? So, you're pulling stuff out of solution. You're pulling the basicity out of it. So, since the basic value is decreasing, what's it becoming more of? It's becoming more acidic. So what will happen to the value of the pH? It'll go down. It'll be not necessarily below 7, just the pH will decrease. Never tell above or below 7. Always either say more acidic or more basic. Never give a value. Well, let me tell you what they have. It says a solution of sodium carbonate is basic. When the carbonate precipitates out, this decreases the pH. Let me tell you how they score the point. 1 point because the carbonate solid precipitated out, which pulled the basic out of it. Because it said sodium carbonate is basic. So when this forms, it's becoming less basic, which means the pH will decrease. You with me? And they said, a solution of sodium carbonate is basic. When carbonate precipitates out, this decreases the pH. 1 point is earned for the correct answer. No explanation is required. So all you have to say, the pH decreased or increased. You don't even have to say. And again, this is a 50-50 shot. Sir.
I was wondering, if you get like a strong acid or strong base mixed together, can you drink that after you drink it?
If you're very, very careful, you better make sure they're 100% the same. I wouldn't do it.
He dies, I'll let him all know you go.
Like, what would happen to the ions? They just go on to
Yeah.
have fun in your body and stuff like that.
Yeah. Depends. I mean, if it's hydrochloric acid, you need chloride ions everywhere. If it's sodium hydroxide, you need sodium ions everywhere. Sodium, potassium pump, move stuff around. It's biology. You'll get there. All right. So, again, I personally feel like some of these are relatively easy if you start knowing write the entire equation, cancel stuff off, and go with what you know. Okay? Y'all feel a little more confident after this? Okay. I know that what I'm going to do is I'm going to go back and I'm going to look at the one from mock. I may pull it out and see if we can go through it question by question. The first one was a complex ion. You were shot in the foot from that point on. And I don't know why they used that question, because nobody knows what complex ions are. And the rest of them we might have could have figured out, okay? All right, so again, thank y'all for coming, and we'll work on qualitative questions tomorrow.